Namaskar my dear friends. Let's talk about current sense amplifier in this session. So what we'll do is we'll try to understand what is current sense amplifier, why how they are important, why they are important actually, where are the applications and how do we use them, what are the different design techniques like circuit design techniques for using them, okay? And we'll see several examples for their industrial and automotive applications as well, okay? Even home appliances are there that is used. So basically let us quickly see what are the different places where current sense amplifiers can be used a lot, okay? So as you can see, if you see infrastructure, so you have like LED drivers or lighting controls or signaling scheme, or you have base stations, wireless base stations. Everywhere you need to be using current sense amplifiers. Similar to that, if you talk about home appliances, then you have, let's say, washing machines, refrigerators, or like ACs, heaters. So everywhere you need to have some motor control or something like that. There you need to utilize some current sense amplifiers, so that you will be using your shunt resistors, and through that you will be sending it to the current sense amplifiers, okay? Even in automotive applications, like you have lot of motor drivers, and where you need to utilize current sense amplifier for sensing the current monitor, or how much current that is flowing through the load. If you talk about factories, you have lot of like robots, or we have some machines like drill machine or something like that. We have printers, or we have lot of BLDC motors, PSMS motor. We have office appliances like printers, or pagers or something like that. So all these places we have to utilize, or we have to have a need of current sense amplifiers. That's the reason we are going to utilize this particular session, okay? So in list wise, if you see quickly, you can have a like application of this current sense amplifiers in like motor control, or battery monitoring, or power management, lighting control. We have overcurrent detections or something like that. Let's say in a line, uh, current is flowing more than the threshold limit, then you can detect with that. We have solar inverters, as I told you, like inverters, chargers, something like that. We have power management monitors, or power monitors, something like that. We have power distributions and safety. We have DC-DC and AC-DC converters, and we have automotive power distributions. So all these places we will be needing current sense amplifiers. So what are the different companies that are producing current sense amplifiers are? You can have many companies other than these as well. So we have like Texas Instruments, then we have ST Microelectronics, we have Analog Devices, we have Renesas, Microchip, Rohm Semiconductor. So basically you can we will be taking one of the application from, let us say, Texas Instrument, or like Rohm Semiconductor. We will be giving you several different manufacturers current sense amplifiers that we have utilized in our several applications for our IPM modules, like let's say intelligent power module for our BLDC motor drives in water pumps, or air conditioner designs, or robotics arms design, something like that. So right now we will consider only one device, and we'll try to explain you through that data sheet how it can be utilized in a particular circuit, okay? So let's get into a particular device which we have selected for this particular session is INA 180, okay? So INA 180 is one device, 218 is two device, and 4180 is four devices, okay? So one device, two device, and four device means one channel, two channel, and four channel are there. So basically if you see particular current sense amplifier, so this can be utilized for your automotive applications as well, okay? And it can be used in both low side as well as high side voltage output, like both side can be monitored. So coming back to the features of this particular current sense amplifier, it can have a range of temperature from -40 degree centigrade to 125 degree centigrade, okay? And it has HBM ESD, that is human body model ESD protection is up to level 2, and it has CDM level is up to, like cardiac level is up to C6, okay? Then it has functional safety system design as well, so so that's the reason it can be utilized in your automotive application. It has a common mode voltage range is up to 26 volt, and it has very good bandwidth as well. So it can give you up to bandwidth of 350 kilohertz. That is A1 device. So it has four types of devices like A1, A2, A3 and A4, and based on the gains they are varying. Like let's say it has a gain of 20, it has a gain of 50, it has a gain of 100, and it has a gain of 200. Okay, so as my gain increases, my bandwidth actually decreases. So from 350 kilohertz it will become like 105 kilohertz. Okay, so this is how the bandwidth will be changing. Okay, coming back to other parts, like we have a slew rate of 2 volt per microsecond, we have very good accuracy which is just plus minus 0.1% gain error. Okay, and as you can see we have gain outputs as I just now told you, like 20, 50, 100 and 200. Okay, let's move to the other part. Let us talk about a typical circuit. So what happens is, let us say we have an input voltage of, let's say, a 24 volt, or let us say 12 volt. Okay, we will be seeing other voltage as well. Like we have lot of current sense amplifier which can take up input voltage more than this, even 65 volt it can go ahead, or 100 volts it can go ahead. Okay, but our aim is to understand what is current sense amplifier and how it can be utilized in a circuit. Okay, so let us say we have a 12 volt input here, and in this case we have a current sense like a shunt resistor, that is sense resistor here. This sense resistor will be connected across this inverting input and non-inverting input of this particular current sense amplifier. Okay, and then it can go ahead with your load circuit. So this particular input is going to take this, let's say the current flowing through this I sense is, let's say I sense, and multiplied by R sense, that will be the voltage drop across this particular input, and that will get amplified based on the gain setting that is there inside this current sense amplifier, and then you will get a voltage output. Okay, now this voltage output is going to go into the ADC, whether it can go into the inbuilt ADC of a microcontroller, or you can send it to a separate external ADC, and there from there it can go to the microcontroller. Okay, and this is how you are going to measure the value of the current flowing through this particular sense resistor. Okay, and this is how you will be able to understand what is the current, what is the amount of current that is flowing through this particular load. Okay, and the other part is there will be a voltage supply to this particular current sense amplifier that will be required to power this up. So it can take up to 2.7 volt to 5.5 volt. So it can be utilized, let's say a 3.3 volt application also, if you want you can utilize. Otherwise 5 volt is generally recommended always, so 5 volt you can give it, so that you have a output range of like up to 5 volt swing. Okay, so if you have a ADC capability of only 3.3 or something like that, then I will suggest you to supply the voltage with 3.3 volt. Okay, let's get into the more details of this particular IC, so that you have a proper understanding of datasheet as well as the other parts. Okay, so if you see packaging information, it has three parts. One is INA 180, as I told you, which is SOT 23 package of 5 pin. Okay, so there are 5 pins, as you can see this one. So this is your SOT 23 package of 5 pin. We have another one VSSOP with 8 pin package that is having 2 channel. Okay, so this is the VSSOP package of 2 channel, and this is my TSSOP package of 14 pin with 4 channels. So basically it will have 4 current sense amplifier, it will have 2 current sense amplifier. Okay, and this will be having only 1 current sense amplifier that is there with SOT package. Okay, let us quickly get into the device comparison. So device comparison, as I told you, like for one channel we have total 8 devices, like 4 devices are A1, A2, A3, A4, that are having actually different gains. Okay, similar to that B type device is also there, which is having same 20, 50 and 100 and 200 gains. Okay, I'll tell you what is the difference between A type and B type. Only the pin configuration change is there, that you can see very quickly. Let me just show it to you. A type, if you see, we have pin configuration like this, like a positive input side is like pin number 3, which is left side, and negative input side is right side, which is minus side, input minus. Okay, so this is my A type. If you talk about B type, then you can see both positive and negative are on same side. That's the like only difference that is there with A type and B type. So actually this particular configuration actually helps us to understand like how to connect these devices based on the different application, whether you are going to measure the high side current sense amplification or low side like current monitoring. So both the kinds of devices can be utilized based on the layout understanding. Okay, coming back to the other parts, we can see we have a 2 channel device and we have a 4 channel device. So 2 channel device, 4 parts are there, and 4 channel device also 4 parts are there with different gains, as I told you about 20, 50, 100 and 200. Okay, let's get into the pin configuration very quickly. So we have GND pin, that is your ground pin. So ground pin is there. Then we have input minus, that is your current sense amplifier negative input. So that can be connected in 2 manners. One will be for high side application, we have to connect this particular pin to the load side of the resistor. So just understand, load side of the resistor we have to connect the negative pin. Okay, we'll show it to you the diagram. Similar to that, for low side application we have to connect this to ground side. Okay, so that's the understanding. Similar to that, for input plus, that is your positive input. So positive input for high side application you have to connect it to the bus voltage, the input supply voltage, as I mentioned just now. This is my input side voltage, so this is a high side application. Okay, if you have to have a low side application, then it will get connected something like this. So positive will come after the load, and the negative will come to the ground, something like that, as it is mentioning here. For low side application, this positive will be connected to the load side of the sense resistor. Okay, now coming back to the output. So output is going to give you analog output voltage, and this is Vs, which is our supply voltage, which can take up to 5.5 volt. So generally it depends on like what is the output voltage that you want to have, like at the full scale level, that much supply you will be giving, either 3.3 volt or 5 volt. Okay, good. So let's talk about absolute maximum rating. So any ICs that we have been studying in our sessions, whether it is amplifier or diode or any other ICs, let's say regulator or microcontrollers or any other IC, if you take, we have always maximum ratings. So maximum rating, the supply voltage, it can take up to 6 volt. The analog inputs, it can take up to plus minus 28 volts. Okay, it can give you output voltage to Vs plus 0.3. Okay, so Vs is 6 volts, so 6.3 it can give you maximum. Okay, we have maximum output current that it can give you is 8 milliamperes. So you have to understand the if more than 8 milliamperes is needed, then you have to have a amplification again at the output of current sense amplifier. Okay, but that is never the case. And we have operating temperature from minus 55 degrees centigrade to 150 degrees centigrade. Let us talk about recommended operating conditions. So in recommended operating condition, if you see, we have a nominal voltage supply of 12 volt, as I was mentioning you. Even if you can utilize, you can utilize it for 15 volt application, or generally 15 volt is always the supply for IPMs or something like that. So there also you can utilize this, or even 24 volt applications you can go ahead and utilize. We have a supply voltage, so nominal voltage is 5 volt that you can give, and we have operating temperature that is minus 40 degrees centigrade to 125 degrees centigrade. That is the recommendation that was there. We have several electrical characteristics, but we'll see what is important, or otherwise you can go ahead with the data sheet and read it very carefully with each and every parameters, but we'll see only the recommended one. Let us say gain. So gain, as I told you already, we have A1, A2, A3 and A4 devices, and their gains are 20, 50, 100 and 200 volt by volt. Okay, let us talk about gain error. So gain error, as you can see, we have a typical value as plus minus 0.1% and maximum is just plus minus 1%. Okay, so you will not be having much gain error. Coming back to the gain error versus temperature, so if you vary temperature to very high value, it is not changing more than 20 ppm per degree centigrade. Okay, so it is just 20 ppm per degree centigrade. Coming back to the non-linearity error, so non-linearity error is very good, which is just plus minus 0.01%, And coming back to the output voltage swing, so output voltage swing you have to understand VSP and VSN. So SP is positive side and SN is negative side. Okay, so coming back to this one, as you can see, this is going to give you maximum Vs minus just 30 millivolt. Okay, that is 0.03 millivolt. So let us say if you have supplied 5 volt, then you will be able to get 4.97 volt maximum. Okay, and similar to that, ground side it will be having 5 millivolt. So what if ground is 0 volt, then you will be minimum getting 0.005 volt. Okay, that is 5 millivolt. So your output swing will be 5 millivolt to 4.97 volts. Okay, we have bandwidth. So bandwidth, as you can see, as my gain is like decreasing, my bandwidth is also as my gain is increasing. As you can see, it is increasing, like A1 is having 20, then 50, then 100 and 200. My bandwidth is actually decreasing. Okay, let's talk about some of the typical characteristics. As you can see, if we talk about gain versus frequency, so as my frequency is increasing, my gain will start reducing a little. Okay, but as you can see, till 100 kilohertz we do not have any like variation in A1 type. Then A2 type, it is little lesser, which is going to be, let's say, 10, 20, like 30, 40, around 50 kilohertz or something like that. So this is how you are getting it. Okay, similar to that, other ones with increase in gain, you can see there is a little bit decrease in the bandwidth, that is the frequency. Okay, and if we talk about gain error versus temperature, we also saw the values. So that was very small, which is less than minus 0.1%. Okay, so as you can see, this is very small. Okay, let's talk about block diagram. So if you see the block diagram, as you can see, we have inverting input pin, we have non-inverting input pin. So here only we have to connect the sense resistor, and this is how it will be connected. So this will be my V input, and this is my R sense, and this is the load that will get connected to the output. Okay, so this is how it will work, and this will get amplified and will give you the output voltage. This is my power supply that will be given V input, okay, or V supply, and this is my ground pin. And the advantage of current sense amplifier is, if you want to use a separate amplifier, you will be needing a set, like a gain setting, like this R1, R2. Let us say I will put it R1, R2, R3 and R4. So we will have to have a requirement of designing all these 4 resistors and set the gain, and there may be a possibility always that with due to the tolerance in the each of the resistors, there will be a difference in the output gain always. Okay, so this becomes little bit tough job. That's the reason they have been inbuilt inside the chip, and you are going to get a particular output. Okay, let's talk about the feature description. So as you can see, we have the features like it has very good high bandwidth, and it has a slew rate. Okay, and it also supports a small signal bandwidth as high as 350 kilohertz, that I have already told you, and it has a large signal slew rate, which is 2 volt per microsecond. Coming back to the application, okay, so let us talk about how we are going to connect this particular current sense amplifier. So we have the inverting input, non-inverting input and inverting input. So let us say high side we are going to connect. Okay, so in high side, this is my supply voltage. So let us say 12 volt application we have. So 12 volt input will be there. Then put your R sense that we will be calculating later on in our design. So generally it may vary, let's say 0.5 milliohm, or like 1 milliohm, or even 10 milliohms or 20 milliohms. So as my current actually decreases, my sense resistor value will be increasing. Okay, so my I value decreases, my R sense value will be increasing. Okay, that's the reason it will maintain the voltage drop across this particular sense resistor, so that you can amplify it properly. Okay, so this was high side type. If you talk about load here, and then low side. So low side, as you can see, to have a low side, you have plus connector at the low side, and then minus is near the ground. Okay, and you have again the same sense resistor. So either this will be one application, or another application will be this one. Okay, so there are two applications that can be there, and in some cases both the sense resistor will be utilized in, let's say, motor drive application or somewhere where high side switch and low side switch both are there, and we need to monitor the current in each one of them. Okay, coming back to the precise low voltage low side current sensing. So as you can see, my offset voltage is just up to plus minus 150 microvolt. Okay, and we have gain error which is much lesser than 1%. Okay, coming back to the rail to rail output swing. So as I already mentioned, the rail output swing was how much? VSP was actually Vs minus 0.003 volt, right? Which was I mean how much? 3 millivolt, or it was I think 30 millivolt. We'll see. And then similar to that, 5 millivolt was from ground side. Okay. But the thing is, in common mode voltage supply, as you can see, common mode voltage supply, as my voltage is increasing, my zero cross current output is actually increasing. Okay, so if my input voltage is little bit higher, the device input voltage is bit higher, then my offset will also be little higher. Okay, so that's the reason if we are working with 12 volt, my value will be little lesser. And these are the four kinds of devices, like this is my A1 type, A2 type, A3 type and A4 type. Okay, I will write it down: A1 type, A2 type, A3 type and A4 type. So as you can see, we have more gain, we have more error. Okay, we have less gain, we have less error. Now let us talk about the functional mode. So this IC is having functional modes like normal mode, which is always we can utilize. We have differential mode as well, where the input voltage difference is actually increasing, which is more than 26 volt. Okay, at the input plus and input minus. Okay, so it can be more than 26. That's the reason we are going to have overload. And we will be using shutdown mode as well, because shutdown mode is utilized whenever we want the IC to keep working. It can keep work, otherwise it can be shut down based on the need. So we'll see one of them. So let us talk about shutdown mode. So shutdown mode, how does it work? Let me just increase this size so that you can understand it very clearly. Okay, so let us say we have a 12 volt bus voltage here, okay, which is coming, and this is the sense resistor which is sensing and going to get into the inverting terminal and non-inverting terminal of this particular current sense amplifier, and we will be getting the output based on the current that is flowing through this across the sense resistor, and this is my load. Okay, so this is high side switching. Now what is happening is, let us say we don't want the output to come. Okay, so that time what we can do is we can shut it down. So let us say we will put it this is my shutdown mode, right? So what is happening, this is my P channel MOSFET. Okay, P channel MOSFET. So what is happening is, this particular supply voltage, let us say 5 volt we are giving here. So 5 volt has been actually biased at this gate also. So this is my gate. So gate is also biased with this 5 volt, so that what is happening is, this is my source and this is my drain, right? Since it is P channel. So this is not on. Okay, now to switch it on, this particular MOSFET, we will have to pull it down, that pull it ground. Okay, so once it comes to the ground, then the source to gate will be a difference, and this is how this will get switched on, and this is how the supply voltage will come to the supply pin. Okay, so this is how you can shut it down whenever you want. You can keep it high, and whenever you want it to work, we can pull it low. Okay, that's the reason. Anyway, by default it will always be in shutdown mode, like whether you give whether you keep it open, your input signal, it will be always open. Let's talk about basic connection. Like we will try to design this circuit quickly and understand how we can calculate different values. Okay, so if you see this particular circuit, we are going to have a very good design here. Okay, so this is the input voltage that I have been talking about, let us say 12 volt. We have to design the value of R sense based on the load that will be taking, or based on the current that it needs, maximum current, let's say I max or something like that. Okay, and what is the power dissipation across this particular sense resistor that we are expecting, or across this particular IC we are expecting power dissipation, and then it will go to the ADC, and then it can be sent to the microcontroller, or otherwise generally microcontroller has inbuilt ADC, so ADC will be inside the microcontroller. Okay, and we'll be giving a voltage supply which will be, let us say, 5 volt. Now to do this calculation we will just try to see the formulas like this. Let us say we have to find out what is the value of R sense. So R sense must be lesser than power dissipation maximum across the R sense, okay, dissipation in R sense, that is sense resistor, divided by maximum current allowed whole square of that. Okay, so a square of maximum current. Okay, so that's the understanding. Coming back to the gain settings and all, so let us say which device we should use, like 20 gain, or 50 gain, or 100 gain, or 200 gain. Okay, so that depends on this one. So let us say we have maximum a swing voltage which is positive side, so this must be greater than the multiplication of maximum current multiplied by R sense into gain. Okay, so this must be smaller or lesser than the VSP. Coming back to SN side, so in VSN side what is happening, this multiplication must be greater than SN. So that's the understanding that you should have, my VSN and my VSP. Okay, so in between your voltage should be there. That's the reason this particular thing is less than VSP and this particular thing is greater than VSN. Okay, so this is the understanding you should have. Your output voltage must lie between VSN and VSP. Okay, now there are some cases where we need input filtering. So in input filtering what happens is we will be requiring a setting of external resistors. So this is a RF resistor, like 2 RF resistor will be there with 1 CF a capacitor, that is filter resistors and filter capacitors. Okay, so these ones will be designed at the input before sending it to the inverting terminal and non-inverting terminal of your current sense amplifier. Okay, so let us say we have 12 volt here, and then let us say we are going to give here 5 volt input. Okay, let me just write it down, 5 volt input, and then we are going to get the output which is going to go to my ADC for your detection. Okay, so you can put a this filter circuit by designing this particular values. So how to design this RF and CF, that is their formula is there in the data sheet. You can have a look in that and design it. Okay, so let me just quickly give you those settings. So we have a gain error factor which can be designed with internal resistor multiplied by 1250 and divided by all these RF value and internal value. So internal is nothing but internal input resistance. Okay, and as you can see, for different devices like A1 type, A2 type, A3 type, A4 type, we have different resistors internally, so we have to take these values into account. Okay, and gain will be correspondingly taken. Okay, so if there is a need of gain, we will be requiring this one. Now coming back to the gain error factor, so gain error factor will be actually already calculated. So if you see, this is the gain error factor for A1 device, A2 device, A3 device and A4 device, and here we will be requiring 21 times RF plus 25,000. Okay, so this is the thing that we will be using. Okay, so let us say we want to find out gain factor of gain error factor of, let us say, 0.5%. so in that case 0.5% will be equal to this one, and from there we will be able to get my RF value, and that's how these RF values will be utilized here. Okay, got it? And if you want to have a gain error in percentage, then that will be equal to what, 100 minus 100 times gain error factor. Okay, so that will be your percentage gain. So as you can see, let us say gain error factor we are getting 0.1, then your gain error percentage will be how much? 100 minus how much it is? It is going to be coming 10, so that is your 90%. So this is very huge, so that will be a problem. So it will not be coming this much. Let us say gain error factor will be coming, let us say 99. So it is going to give you 100 minus 99, so that is going to give you just 1%. Okay, so this is how you will be getting. So gain error factor will be little bit higher. Coming back to the other part, let us design one. As I mentioned, all the formulas you have already seen. Just now I showed it to you, like how to design the value of R sense, or like how to get the value of gain, or all these things. So we can have a application, and it will give us an understanding how to design the circuit. Okay. So very first thing, in the datasheet itself there was a design parameter given, and one design is also given. We'll just give you an explanation so that you can understand how to utilize or how to extend the same concept in your next designs with other ICs, or like other applications as well. Okay. So basically we have a power supply voltage which is 5 volt, okay, and we have low side current sensing which is 0, okay, and then R sense power loss is 900 milliwatt or lesser than that. So we have to have a understanding of power dissipation across the R sense value is must be less than 900 milliwatt. Then maximum current across the sense resistor is 40 amperes. So this is huge. Generally this much will not be needed, and anyway this is our design parameter, and we have current sense error as less than 1.5%, and we have a small signal bandwidth which is greater than 80 kilohertz. Okay. So anyway we will be utilizing any of the 4 devices, let's say A1 or A2 or A3 or A4, and we'll try to see which one is more suitable compared to this. And anyway, if you see, signal bandwidth is, even A4 has 105 kilohertz, so that is not a problem, and this is having 350 kilohertz. Okay, so this is good part, no problem. So let's do the calculation. So what is the first calculation that we should do? First we should calculate the value of R sense, okay, and then we should choose the device that we will be needing for this particular application. Okay. So this is my supply voltage, and we have a load that is connected, and we have a requirement of R sense that we are going to calculate. And as you can see, since it is low side application, so positive is connected after the load and negative is connected towards the ground. Okay. And we will be requiring, let us say, 5 volt supply. So this is how we will be connecting with one decoupling capacitor of 0.1 microfarad. Okay. Now let us design the R sense value. So once we have R sense value, you have the formula of PD max by I max square. So PD was 900 milliwatt divided by 40 square. So that was like in ampere. So this will become milli ohms. So if you see, it is coming to be 0.56 milli ohms. So my R sense must be lesser than that. So closure value or standard value is 0.5 milli ohms. So 0.5 milli ohm we are going to choose. Coming back to the gain value, so gain value we can do here. So that will be how much? VSP divided by these two values. So if you do that, let us say VSP is 5 divided by 40 multiplied by 0.5 milli ohm was there. So that will go and becomes 10 to power 3. Okay. So this is how we are going to get 250 gain. So if we are getting 250 gain, we can go ahead and choose a like a current sense amplifier with highest gain, which was 200, which was A4 device. Okay. So that's all. This is all done. Coming back to the other part, let us say how we can save our device. So the thing is, if you want to have a transient protection, let us say we have here 12 volt input, but there is a transient that is keep on coming. Okay, so in that case what happens is, R sense resistor is there that was designed, we have a load, and we have like a resistor which is going to have a R protect resistor, which will be like if you want, you can put it, let's say 4.02 ohm both of them. Okay, 4.02 ohm both of them, or maybe like 5 ohm each one of them. Okay. Now coming back to the protection. So protection, you can utilize Zener diodes to protect them. So from ground you can see we have a Zener diode here, and we have a Zener diode at this place. So negative input also and positive input also, both the places we will be using one Zener diode connected to ground. Okay. So that's the understanding. We are going to save our device from the transient protection. Okay. So this is how connect a Zener diode Z1, let us say, and Z2 to the ground from your inverting terminal and non-inverting terminal of your current sense amplifier, and this is how you will be protecting from transient at the inputs. Okay. And let us say this is your 5 volt. Coming back to another process, so there is another process as well. You can utilize bidirectional ESD diode, okay, which will be connected at the negative terminal, okay, and there will be two side by side Zener diodes which will be connected between an inverting terminal and non-inverting terminal. Okay, so this is how also you can utilize using your trans absorption or as well as input clamp. So these two are actually clamp voltages, and this is how you will be saving the or protecting the input of this particular current sense amplifier. Okay, hope you have now a good understanding about this particular current sense amplifier and how to design the circuit. Let us now just close our discussion with the layout guidelines. So in layout guidelines, if you see, we have a positive terminal of current sense amplifier and negative input terminal of current sense amplifier. So between these two you can connect your R sense. Okay, and we have here input voltage which is, let's say, 12 volt, and we have this side as load. Okay, so this is how it will be connected. Coming back to the supply pin, so supply pin, you can give a supply voltage here, and then it will be connected through a decoupling capacitor or bypass capacitor via ground is plane is there, and it will get connected to the ground below the IC. So this is must that you have to understand, and this will be taking the output which is going to go to the ADC of your microcontroller. Okay, so good. Hope you guys have understood what is current sense amplifier and how important they are in different applications, and how we are going to utilize them for our different applications in industrial applications or automotive application, or like home appliances, let's say like HVAC application like heating or ventilation or air conditioner or motor drivers. So there are a lot of things where like current sense amplifiers are needed, because we have shunt resistors which need to be monitored how much current is flowing through that shunt resistors. Okay, so if you have any questions or any understanding requirement regarding this current sense amplifier, or how to choose them or how to utilize them, please put down your comments in the comment box, or questions, queries in the comment box, and we shall be able to give you answers as soon as possible. And if you are liking our understand sessions, you please subscribe and like our videos. Thank you so much.